So today it's again a brand new topic. So if you like relativity, you would be in grief and mourning. If it got to be really nasty, you will be relieved that that's behind us now. And let me remind you one more time that the problem set for relativity was quite challenging because I had to make up most of the problems. And they are not from the book, so they're a little more difficult. The exam will be much more lenient compared to the homework. That's generally true, but particularly true in this case. Okay, so today I'm going to introduce you to some mathematical tricks. As you probably noticed by now, a lot of physics has to do with mathematics, and if you're not good in one, you're not going to be good in the other. And I just thought I will spend some time introducing you to some tricks of the trade, and then we will start using them. First important trick is to know what's called a Taylor series. Okay, I see this is greeted by boos and hissing sounds. I'm not sure what your past experience with Taylor series was and why it leaves you so scarred and unhappy. My experience with Taylor series has been positively positive, and I don't think I can carry on any of my things without knowledge of Taylor series. But I'll tell it to you, Taylor series, as we guys in the physics department tend to use it. The philosophy of the Taylor series is the following. There is some function f of x. And I'm going to draw that function, something like this. But I'm going to imagine that you don't have access to the whole function. You cannot see the whole thing. You can only zero in on a tiny region around here. And the question is, as you try to approximate, as you try to build a good approximation to the function, how will you set it up so that you can write an approximation to this whole function valid near the point x equal to 0, where you know something? So suppose I block out the whole function. You got to imagine mentally. I don't show you anything except what's happening here. In other words, I show you only f of 0. That's all you're told. The value of the function is 92. What should we do away from x equal to 0? Well, you got no information about this function. You don't know if it's going up, if it's going down. All I tell you is one number. What it's doing now is clear. The best approximation you can make is a flat line. There's no reason to tilt it one way or the other given the information you have. So the first approximation of the function you will say is f of x equal to that. It's not equal to. You can put some symbol. That means approximately equal to. But then if you have, it's like saying temperature today is 92. What's it going to be tomorrow? Well, if you don't know anything else, you cannot tell what it's going to be tomorrow. But if you know that this is fall and the temperature is always going down, and somebody tells you, I know the rate of change of temperature. I know that today the rate of change of temperature is something. Then you can use that information to make a prediction on what it will be tomorrow. That is to say, for values of x not equal to 0. And let's denote by this following symbol. F prime of 0 is the derivative, which is df dx at x equal to 0. And you'll multiply it by x, and that's your best bet for what the function is away from x equal to 0. What that does is to approximate the function by a straight line with the right intercept and the right slope. By right, I mean matches what you know about the exact function. And if it turns out the function really was a straight line, you're done. It's not even an approximation. It'll track the function all the way to eternity. But it can happen, of course, that the function decides to curve upwards, as I've shown in this example. And this will not work if you go too far. For a while, you'll be tangent to the function, but then it'll bend away from you. So it's really good for very small x, and you can say, well, I want to do a little better when I go further out. Well, what this doesn't tell you, this approximation, is that the rate of change itself has a rate of change. This assumes the rate of change is a fixed rate of change, which is the rate of change at the origin. And the rate of change of the rate of change is the second derivative. So if somebody told you, look, here's one more piece of information. I know the second derivative of the function, which I'm going to write as f double prime at 0. Well, with that information, you can build a better approximation to the function, and you will put that in x squared. But the key thing is you got to divide by 2, or if you like, 2 factorial. Now, why do you divide by the 2 factorial? Because your goal is to take this approximation and make sure it has whatever you know about the function built into it, right? Let's check this approximation and see if it satisfies those properties. First of all, at x equal to 0, let's compare the two sides. At x equal to 0, the left-hand side is f of 0. On the right-hand side, when you put x equal to 0, you kill this and you kill this, and it matches. So you certainly got the right value of the function. Then you say, what if I take the derivative of the function at x equal to 0? Let's take the derivative of this trial function or the approximate function on both sides. When I take the derivative, that being a constant does not contribute. This derivative of x is 1. In the next one, derivative of x squared is 2x. 2x cancels the 2. So I get f double prime of 0 times x. But now evaluate the derivative at x equal to 0. Then that gets rid of this guy. And the derivative of my test function matches the derivative of the actual function, because this is the actual derivative of the actual function. Now it follows that if you want to say, how about the second derivative of this function? Let's take the test function I have, or the approximation, take its second derivative, and make sure that comes out right. I don't feel like writing this out, but try to do this in your head. Take 2 derivatives on the left-hand side, and see what happens on the right-hand side. Well, if you take 1 derivative, this guy is gone. If you take 2 derivatives, this guy is gone. And then if you take the first derivative, you get 2x. If you take the second derivative, you get 2. The 2 cancels the 2. Now you put x equal to 0. If you do, you find that f double prime 0 here matches the second derivative of the function on the left-hand side. So this 2 factorial is there to make sure that the function you have cooked up has the right value of the function at the origin, has the right slope at the origin, has the right rate of change of the slope at the origin. Well, it's very clear what we should do. If you had a whole bunch of derivatives, then the approximation we will write will look like f nth derivative. I cannot draw n primes there, so n means n such primes. X to the n over n factorial. And you go as far as you can. If you know 13 derivatives, put 13 derivatives here. That's an approximation. That's not called the Taylor series. That's the approximation to the function. Now it may happen that sometimes you hit the jackpot and you know all the derivatives. Someone tells you all the derivatives of the function. Then why stop? Just add them all up. Then you will get the sum going from the 0 derivative all the way up to infinity. And if you do the summation at every value of x, you'll get a value. And if that summation is meaningful and gives you a finite number, that in fact is exactly the function you were given. And that is the Taylor series. The Taylor series is a series with infinite number of terms, which if you sum up and sum up to something sensible, will actually be as good as the left-hand side. So let me give you one example. It's a famous example. 1 over 1 minus x is the real function, okay? You and I know this function. We know how to put it in the calculator. We know how to plot it. You give me an x and I stick it in the denominator, subtract it from 1, invert it. That's the function. But instead, suppose this function was revealed to us in stages. We were told f of 0. What is f of 0 here? Put x equal to 0. F of 0 is 1. Now let's take the derivative of this function, df dx. df dx has a minus 1 because it's 1 minus x to the minus 1 times a square. Then the derivative of what's inside this, that gives you a minus 1. This is simple calculus, how to take the derivative of this fellow here. Having taken the derivative, evaluated at x equal to 0, this vanishes, that becomes 1, and you get 1. If you now take the second derivative of this function, which I don't feel like doing, and I evaluate that at x equal to 0, and I'll find it is equal to 2 factorial. In fact, I'll find the nth derivative at the origin to be n factorial. Well, that's very nice, because then my approximation to the function begins as 1 plus x times the first derivative, which happens to be 1, plus x squared over 2 factorial times the second derivative, which happens to be 2 factorial, plus x cubed over 3 factorial times 3 factorial. So you can see where this guy is going. It looks like 1 plus x squared, etc. The Taylor series is this infinite sum. In practice, you may be happy to just keep a couple of terms. So let's get a feeling for what this couple of terms can do for us. So let me take x equal to 0.1. X equal to 0.1. The real answer is 1 over 1 minus 0.1, which is 1 over 0.9, which is 1.1111, etc. That's the target. What do you do with the series? The series starts at 1 times 1/10 plus 1 over 100 plus 1 over 1,000, and so on. And you can see, as I keep more and more terms, I keep just filling up these ones. If you stop with 1 over 1,000, you stop right there. So this is the exact answer. This is the approximation. But it's clear to you, perhaps in the simple example, that if you kept all the terms in the series, you really will get this infinite number of recurring ones. So that is the function. That is the Taylor approximation, which is chop it off whenever you want, and it's a good approximation. And that's the Taylor series. The series means sum everything. Now, summing an infinite number of numbers is a delicate issue. I don't want to go there at all. I discussed that in this math book. But sometimes the sum makes no sense, then you got to quit. For example, put x equal to 2. The correct function is 1 minus 2, which is minus 1. Our approximation for x equal to 2 looked like 1 plus 2 plus 4 plus 8. And first of all, this sum is going to grow to infinity because the numbers are getting bigger and bigger. This sum seems to be all positive, whereas the correct answer is negative. Obviously, the series doesn't work. So the next lesson about Taylor series is you can write down the series, but it may not sum up to anything sensible beyond a certain range. So if you're doing the Taylor series at x equal to 0, and you go to x equal to 2, it just doesn't work. So you can ask, how far can I go from the origin? Well, in this simple example, we know that at x equal to 1, the function is just going to infinity. That's why you couldn't go there. And you cannot go to the right-hand side of that point. The function is well defined on the other side, but this series, this knowledge of the function here is not enough to get you on the other side. So this is a case where there are obvious problems at x equal to 1. But if I wrote a function like 1 over 1 plus x squared, that's a nice function. Got no troubles anywhere. And yet, if you took the Taylor series for it, you will find if you go beyond absolute value of x equal to 1, the series makes no sense. So I don't want to do the mathematical theory of series. I just want to tell you that functions can be approximated by series. And if you're lucky, you can do the whole sum if you know all the derivatives. And the whole sum may converge to give a finite answer, in which case it's as good as the function. One guy can use 1 over 1 minus x, the other one can use the infinite series, and they're morally and mathematically in every sense equal as long as they don't stray outside the region of validity of the infinite series. Okay, so the most popular example that I've been using in the class, you remember, is 1 plus x to the n. That's a function. We can do its Taylor series. F of 0 is 1. What's the derivative of the function? It's n times 1 plus x to the n minus 1, right? df dx is n times 1 plus x to the n minus 1. If I evaluate it at x equal to 0, it is just n. That's why we get this famous result we've been using all the time. if x is small enough, you stop there because the next term is going to involve an x squared and an x cubed. And if x is tiny, we have no respect for x squared and x cubed. We just cut it off. But if you want the next term, one of you guys even asked me, what happens next? Well, take the second derivative. You can see it's n times n minus 1 times 1 plus x to the n minus 2. If you put x equal to 0, you'll get n times n minus 1 x squared. And don't forget the 2 factorial. So what I've been doing is I've been saying 1 plus x to the n approximately equal to this. But even if you keep that, it's still approximate. But it's a good approximation. How many terms you want to keep depends on how tiny x is. Okay, so it's good to know there's an infinite series, but it's also good to know you can chop it off and do business with a few terms. In fact, all of relativity we reduced as follows. The energy of a particle is this, which we can write as mc squared times 1 minus v squared over c squared to the minus 1/2. If you expand this in a power series, you're going to get mc squared plus 1/2 mv squared plus stuff involving v to the 4th over c to the 4th times c squared. We dropped all this, and for 300 years, we did mechanics keeping just this term. We just kept that first non-trivial term, and all our collisions and so on that we did used only that up to that point. So the approximations are very, very useful, and they describe nature approximately. If you say, well, I want to be exact, you can go back and use this. Unfortunately, general relativity tells you that's not exact either, and quantum mechanics tells you the whole thing is wrong. So at every stage, you will have to give up something. So I have a lot of respect for approximations. If you could not describe the world approximately, you couldn't have come where you've come, because no one knows the exact answer to a single question you can pose. Ask me a question, and the answer is, I don't know. Second part of the answer is, nobody knows. Because if your question says, give an answer to arbitrary precision to any question I ask, we just don't know. Newtonian mechanics works for small velocities. All of relativistic mechanics works for any velocity, but not for very tiny objects. Then you got to use quantum mechanics. So always theories give way to new theories, and so approximations are very important. So you have to learn this. Okay, so now I'm going to consider the following function, e to the x. Now this guy is something you all know and love, because it's one nice thing about the function is every derivative is e to the x, right? Every child knows e to the x has got e to the x as its derivative. Why do we like that here? That means all the derivatives are sitting in front of you. They're e to the x, and at x equal to 0, e to the 0 is 1. So every derivative is 1. Then the function is very easy to write down. It is really 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial, x to the 4 over 4 factorial. You can go on like this, and if you like to use a compact notation, is x to the n over n factorial, and going from 0 to infinity, 0 factorial is defined to be 1. That's e to the x. If you ever forget the value of e, and I need to know the value of e because when I lock my suitcase and check it into the airport, I use either e or pi, because they're the only two numbers I can remember. So if I forget the value of e, I just say e is the same as e to the 1. So I got 1 plus 1 plus 1 over 2 plus 1 over 6. And pretty soon I'm telling the guy scanning my luggage, that's my code. And it's much better than any other code because I cannot reconstruct, say, my grandfather's name. May not get it right, or may not construct my house address or my phone address. This doesn't change. I've been moving around all over the world. This is a very reliable number. Now, pi is a good number, but rules for computing pi are somewhat more difficult. Pi also can be computed as an infinite series, but this guy is very easy. That's 2.77 something. That is e. Okay. Now, here is the very nice property of this series. It is good for any x. Remember, the series for 1 over 1 minus x crashed and burned at x equal to 1. This series, always good. You put x equal to 37 million, you got 37 million cubed 30 to the fourth power. Don't worry. These factorials downstairs will tame it down and make it converge and will give you e to the whatever number I gave you. That's something I'm not proving, but the series for e to the x, no limits on validity. All right, then we take the function cosine x. Now, cosine x we all know and love is this guy. Has got a period of 2 pi. But we can write a series for it because it's a function. And what do I need to know to write the series for it? I need to know the value of the function at the origin. So we know cosine of 0 is 1. If you take the derivative, you get minus sine, and its value at 0 is 0. You take the one more derivative, you get minus cosine 0, which is minus 1. And I think by now you get the point. Every other derivative will vanish, and the remaining derivatives will alternate in sign from 1 to minus 1. That means if you crank it out, you will get 1. You won't have anything linear in x because the coefficient of that is sine 0, which vanishes. Then you'll get x squared over 2 factorial plus x to the 4 over 4 factorial, and so on. This is cosine x. If you cut it off after some number of terms, it's not going to work. In the beginning, 1 minus x squared looks very good. This is 1 minus x squared over 2 will look like this, but eventually this approximation will go bad on you because x to the 4th is just x to the 4th. It will grow without limit. No one's telling you this approximation has a property that cosine is less than 1. It doesn't satisfy that because you're not supposed to use it that far out. But if you keep all the terms, then in fact, even though x to the 4th is taking off, x to the minus 6 is saying, hey, come down, x to the 8th is saying, go up. You add them all together, remarkably, you will reproduce this function. Very hard to imagine that the cosine that we know as oscillatory is really this function. And I hope all of you know enough to know how to find this series. You should know the derivative of cosine is minus sine, and the derivative of sine is cosine, and evaluate them at the origin. I say you can build up the series. Then if you do similar tricks for sine x, sine of 0 is 0, derivative of sine is cosine, and cosine of 0 is 1. So the first derivative is 1. That gives you this term. Next one won't give you anything. The one after that will give you this. And this guy will go on like this one. OK, so these are series for e to the x, cosine x, and sine x, good for all x. So there's no restriction on this. One of the really interesting things to do when you're bored or stranded somewhere in an airport is to take cosine squared plus sine squared. You know, square the whole thing, add the square of the whole thing, and add them up. You will find by miracle, you will get the 1 from the squaring the 1, and every other power of x will keep on vanishing. Of course, you will have to collect powers of x by expanding the bracket, but they will all cancel. That's what I meant by saying this series is as good as this function. It will obey all the identities known. OK, now for the punchline. I think some of you may know what the punchline is. The punchline is the following. Let us introduce, without any preamble right now, the number I, which is the square root of minus 1. All I expect of I is that when I square it, I get minus 1. If I cube it, I cubed is I squared times I, so that's minus I, and I to the 4th is back to plus 1. Because I to the 4th is I squared times I squared, and I squared is minus 1. So if you take powers of I, it will keep jumping between these values. It will be I, it will become minus 1, it will become minus I, then it will become plus 1. That's the set of possible values for powers of I. It will be one of these 4 values. Well, then we are told, if you now consider the following rather strange object, e to the ix. Now, e to the ix, you have to agree, is really bizarre. Okay, e is some number. You want to raise it to 2, that's fine. Number times number. I is a strange number, right? It's the square root of minus 1. And you want me to raise e to a complex power. What does that even mean? Multiply e by itself ix times, well, that definition of powers is no good. But the series for e to the x defines it for all x. Then we boldly define e to the x for even complex values of x as simply this thing with ix plugged in place of x. And by that fashion, we define exponential. So the exponential function is simply defined as, suppose you write e raised to dog. E raised to dog is 1 plus dog square over 2. That's the e raised to anything is a code for this series. And now we raise e to various things, real numbers, complex numbers, matrices, whatever you want. Your pet, you can put that up. Of course, you got to be a little careful. You cannot raise e raised to dog because the units don't match. Because there is a dog here and dog squared, so you should have divided by some standard dog. You know, like the president's dog. Take some standard, Napoleon's dog, divide it, then you got something dimensionless, then it will work. So as long as there is some dimensionless object, this is what we mean by e raised to that. That's a fantastic leap of imagination. How to raise e to whatever power you like, take the series. Well, let's do the series, okay? So I'm going to get 1 plus ix square over 2 factorial plus ix cubed over 3 factorial, and I'm going to stop after this last term, ix to the 4th over 4 factorial. Keep going. Then what do you get? Let's take the 1 from here. Leave this alone for a minute. You write I times x. Go here. I squared is minus 1. So I get minus x squared over 2 factorial. Then I come here. I cubed is minus I. So I write here minus x cubed over 3 factorial. Then I go back here and write x to the 4th over 4 factorial. By now everybody knows what's going on. Everybody knows that this is just cosine x plus I sine x. Okay, this is a super duper formula. Life cannot go on without this. You want to draw a box around this one? Draw it, because without this formula, we cannot do so many things we do. It says that the trigonometric functions and the exponential functions are actually very intimately connected. And if they're all defined by the power series, you are able to prove this. So this is the formula proven by Euler. And it's considered a very beautiful formula. And here is the particularly beautiful special case of this formula. If you put x equal to pi, I get the result e to the I pi equal to cosine pi, which is minus 1, plus I sine pi, which is 0. So I get the result e to the I pi plus 1 equal to 0. Now, everybody agrees this has got to be one of the most beautiful formulas you can imagine involving numbers or in mathematics. Why is it such a great formula? Look at this formula here. Pi defined from the Egyptian times as the ratio of circle to diameter. I square root of minus 1. 1 is the basis for all integers. E is the basis for the logarithm. Here's a formula in which all the key numbers appear in one single compact formula. So people think the fact that these numbers would have a relation at all is staggering, and this is the nature of the relationship. This is voted the formula most likely to be remembered, this formula. Now we are going to use not only the special case, but we are going to use this all the time. So you guys have to, so how many people have seen this? Okay, if you have not seen this, then you got more work than people who have seen this. You got to go and you got to do all the intermediate steps so you get used to this thing. Now let's do the following 2 other variations and then I'll move on. If I change x to minus x, then I get e to the minus ix. Cosine of minus x is cosine x, and sine of minus x is minus sine x. So I can get that relation. Then I'm going to combine those two to do the following. I'm going to say that cosine x is equal to e to the ix plus e to the minus ix over 2. You can check that. And sine x is equal to e to the ix minus e to the minus ix over 2I. You just add and subtract these two formulas, and you get that. Okay, so what does this mean? It means that trigonometric functions, you don't need them. If you've got exponential functions, you can manufacture trigonometric functions out of them, provided you're not afraid to go to exponents with complex number I in them. And all the identities you know about sines and cosines will follow from this. For example, if you take cosine square plus sine square, you're supposed to get 1. Well, you can square the right-hand side, you can square the left-hand side, and you will get 1. To get the 1, you better remember the following. E to the ix times e to the minus ix is what? You know how you combine exponents. You raise it to one power times the same thing raised to another power is e raised to ix minus x, which is e raised to 0, which is 1. So when you raise the number to a power, you multiply it by the number times a different power. The product is the number to the sum of the two powers. Right? Powers combined. 2 cubed times 2 to the 4th is 2 to the 6th. That's true for 2, it's true for e, it's true for everything. Exponents add when you multiply them. That's why e to the ix and e to the minus ix combine to give you 1. Once you know that, you can prove this. Okay. Now I'm going to do a little more of complex numbers. Maybe I'll leave this alone for now. So I introduced you the number I by saying it's a square root of minus 1, and complex numbers entered our life even though we didn't go looking for them. You can write down equations with real numbers with no intention of invoking anything fancy like this, and you find there is no solution to this equation, even though everything there is completely real. Or, so you can say, well, x squared is minus 1, and you can manufacture a number I with the property I squared is minus 1, then of course you can have x equal to plus or minus I as your answer. So complex numbers arose by trying to solve quadratic equations. So let me write you a slightly more interesting quadratic equation. X squared plus x plus 1 equal to 0. So there's no funny business, all real numbers. We want to solve this equation. So we go back to our good old sandbox days when we knew what the answer for this was. Minus 3 over 2. And we already have a problem because we don't know what to do with square root of minus 3. So we will write it as square root of minus 3. We'll write it as square root of minus 1 times square root of 3. Square root of minus 1 we will call I, and we will say this equation has two roots. X plus or minus 1, x plus minus are the two roots, which are minus 1 plus or minus square root of 3I over 2. So one root is 1 minus 1 plus root 3I over 2. The other root is minus 1 minus root 3I over 2. These are solutions formally to this equation in the following sense. Take this x that I'm giving you, put that into that equation, square the x and add the x to it and add the 1, it will in fact satisfy the equation. All you will have to know when you manipulate it is that I squared is minus 1. Using the 1 property, you can now solve the quadratic equation. So people realize that if you enlarge the numbers to include complex numbers, then you can solve any polynomial equation with that many number of roots. If it's quadratic, it will have 2 roots. If it's cubic, it will have 3 roots. They may not all be real. They may involve the complex number I. Now, very important point to notice is that this whole thing, minus 1 plus root 3I over 2, the whole thing is a single complex number. Don't think of it as a sum of two numbers. It's a single complex number. For example, if this had been plus instead of minus, you'd get something like 1 plus or minus root 3 over 2. Take the positive root. You don't think of it as two numbers. This is a single number. And that continues to be true even if it's a complex number. So you should think of the whole combination as a single entity, which you can add to other such entities and square and so on. Okay, so that's what we are going to do now. We're going to generalize this particular case and introduce now a complex number z, and we're going to write every complex number z as a part that has no I in it and a part that has an I in it. The example I had here, x is equal to, in this example, x was minus 1 over 2 and y was plus or minus root 3 over 2. And we're going to visualize that complex number as a point in the xy plane. You just measure x horizontally and y vertically, put a dot there. That's your complex number z. Then we say a new complex number called z star, and it's defined to be x minus iy. It's called the complex conjugate. Complex conjugate of z is obtained by changing the sign of I. So if you like, if z is sitting here, z star is sitting there, reflected on the x-axis. Okay, so how does one work with complex numbers? You add them, you subtract them, and you multiply them, and you divide them. If you know how to do that, you can do with complex numbers everything you did with real numbers. So if z1 is a complex number, that is equal to x1 plus iy1, and z2 is a complex number, that is x2 plus iy2, we will define z1 plus z2 to be x1 plus y1 plus I times, I'm sorry, x1 plus x2 times I times y1 plus y2. If you draw pictures, then if z1 is that number and z2 is that number, then z1 plus z2 really is like adding vectors. This number is z1 plus z2. It's exactly like adding vectors. But you don't think of this plus that as two disjoint numbers, but as forming a single entity. In a complex number z, x is called the real part of z and is denoted by symbol real z. If you want to get z, if you want to get the real part of a complex number z, you add to it as complex conjugate and divide by 2. Because you are adding x plus iy to x minus iy, you get 2x, and you divide by 2, you get that. If you want to get the y, which is called the imaginary part of z, you take z minus z star and divide by 2i. It's like saying find the x component of a vector. It's whatever multiplies I. Y component of a vector is whatever multiplies j. Similarly, a complex number can be broken down into the part which is real and the part that multiplies I. To extract the real part, add to it the conjugate and divide by 2. To extract the imaginary part, subtract the conjugate and divide by 2i. Again, if you have seen this, you don't need this. If you haven't seen it, it may look a little fast, but that's why I posted on the notes on the website chapter 5 from this math book, which has got all this stuff. So you can go home and you can read it. Okay, the next question is, what is z1 times z2? Well, that's very easy to calculate. x1 plus iy1 times x2 plus iy2. Well, just open out the brackets and remember I squared is minus 1. That's all you got to do. So that gives me x1, x2. Then let me multiply the iy1 times the iy2, and that gives me minus y1, y2. Because I squared is minus 1, plus I times x1, y2 plus x2, y1. This is how we multiply two complex numbers. There's something very nice that happens when you multiply a number z by its complex conjugate. What happens when you multiply z by its conjugate? You are saying take x plus iy and multiply by x minus iy. Now, a plus b times a minus b is a square minus b square. But remember, b is iy. So when you take the square of that, you should keep track of all the signs, and you will find it's x squared plus y squared. We denote that as this, and this thing is called the modulus of z. It's the length of the complex number z. It's just given by Pythagoras' theorem. You should know, whenever you take a complex number, multiply by its conjugate, by its complex conjugate, the result will be a real number equal to the square of the length of the complex number. Because I'm going to use that now to do the last of the manipulations, which is what is z1 divided by z2? How do you divide these crazy numbers? So on the top, I write x1 plus iy1. The bottom, I write x2 plus iy2. If I only had x2, I know how to divide. It's just a number. Divide that by x2 and that by x2. But I got the sum of these two numbers in the bottom, and you can ask, how do you do the division? So the trick always, when you run into this problem, is to multiply the top and bottom by the complex conjugate of the bottom. Multiply by x2 minus y2, top and bottom. Then something nice happens in the denominator, because the denominator then becomes x2 squared plus y2 squared, which is an ordinary real number, nothing complex about that. The numerator, you can open out the brackets. I don't know if I want to do that. It's just going to be x1, x2 plus y1, y2 plus I times y1, x2 minus y2, x1. Now, don't worry about all the details. All it means is if you know how to multiply two complex numbers, you can also divide by a complex number. That's the key point. Why? Because if you got a complex number denominator, you don't like it, multiply top and bottom by the complex conjugate of this guy, the denominator turns into a purely real number. So this whole thing could be 36, for example. Well, we know how to divide the numerator by 36, right? x1, x2 plus y1, y2 is some number, maybe 9. Then you divide by 36, 1/4. This could be I times 18. Divided by 36, you get I over 2. So this number could have been 1/4 plus I over 2. So dividing by a complex number is not a problem. Okay, so now, why did I do all that stuff today about e to the ix? You're going to see that now. The rationale for going through that math is the following. So let's take this complex number that goes from here to here, that is x plus iy. And let's introduce, just like we would for an ordinary vector, this angle theta and that length r. Whenever you have a vector, you can talk about the Cartesian components x and y, or you can talk about the length of the vector and the angle it makes. Then it's clear that x is equal to r cosine theta and y is equal to r sine theta, where theta is now an angle associated with a complex number, which tells you at what angle it is located, and r is the length of the complex number. So this is called the polar form of the complex number. Then you can see that z, which is x plus iy, is equal to r times cosine theta plus I sine theta, which you can now write as r times e to the I theta. That's why we did all that work, to tell you that a complex number can be written in this form. You can either write it as x plus iy or as r e to the I theta. They both talk about the same number. One talks about how much real part and how much imaginary part it has. Other way of writing it talks about how long the vector is and at what angle it is located. They contain the same information. So that r is equal to, if the inverse of this formula is that r is square root of x squared plus y squared, and theta is tan inverse y over x. In other words, tan theta is y over x. This is y and this is x. Now, the advantage of writing a complex number in polar form is the following. Suppose I give you two complex numbers. z1 is r1 e to the I theta 1, and z2 is r2 e to the I theta 2. The product z1, z2 is very easy to calculate in this form. Because R1, R2 multiply to give you this, and the exponentials combine. It's a lot easier to multiply them in this form than when I multiplied them somewhere here. See, if you write it in this Cartesian form, it's a big mess. In polar form, it's very easy. So the rule is, if you want to multiply two numbers, multiply their lengths to get the length of the new number, and add their angles to get the angle of the product. So what I'm telling you is that if Z1 looks like this guy with some angle theta 1, and Z2 is that guy with an angle theta 2, the number Z1, Z2 has a length equal to product of these two lengths and an angle equal to sum of these two angles, so it will look like that. To go from this to that, you multiply the lengths and you add the angles. So the polar form is very well suited for multiplying, and it's even better suited for dividing. If I say, give me Z1 over Z2, well, you can all do that in your head. It's R1 e to the I theta 1 divided by R2 e to the I theta 2. The modulus of the new number is just R1 over R2. And how about this? E to the I theta 1 divided by e to the I theta 2. Dividing by e to the I theta is same as multiplying by e to the minus I theta. So this is really e to the I theta 1 minus theta 2. So I'm assuming you guys can figure this part out. 1 over e to the I theta is the same as e to the minus I theta. Well, if you doubt me, multiply, cross multiply, and all I'm telling you is that 1 equals e to the I theta times e to the minus I theta, which you know is true when you combine the angles. So when you got e to the I theta downstairs, you can take it upstairs with the reversed angle. And that's a useful trick. I hope you will remember that useful trick. So there's one part of this thing that I want you to carry in your head, because it's very, very important. When you take a complex number, it's got a length and it's got a direction. When you multiply a second by a second complex number, you are able to do two things at the same time. You're able to rescale it, and you're able to rotate it. You rescale by the length of the second factor, and you rotate by the angle carried by the second factor. The fact that two operations are done in one shot is the reason complex numbers play an incredibly important role in physics, and certainly in engineering and mathematical physics. Okay, I'm going to now change gears, but I want to stop a little bit and answer any questions any of you have. So how many people have seen all of this before? I see. So if you saw something, you saw the whole thing. But look, that's not such a big number, so I am cognizant of the fact that not many of you have seen it. But you will have to go and learn this today. I'm going to post the problem set for this sometime in the day so you can start practicing. Don't wait. Problem set has nothing to do with next Wednesday. It has a lot to do with today. So when I assign a problem today, I imagine you're going breathlessly to your room, not able to wait, jumping into the problem set and working it out. Because that's the only way you're going to find out what these things mean if you've never seen them. If you've seen them before in high school or taken a math course and you've got lots of practice, then I'm not talking to you. But I'm going to use this at some point. So you should understand complex numbers. And I'm telling you, there are very few branches of any science where complex numbers will not be used. You may not believe this now, but that is true. If an electrical engineer, absolute must. If you solve any kind of differential equation, which can occur in biology and chemistry, that's a must. So it's very, very important. All right, so now I'm going back to physics now, going back from mathematics to physics. And the physics of this topic for today has to do with something very different from the past. So forget all relativity. Now we are going back to Newtonian days. Kinetic energy is 1/2 mv squared. So it's a little difficult to go back and forget what you learned. On the other hand, for some of you, it may not be so hard. If you didn't learn anything, then you are that much ahead of the other guys. Okay, but so remember now, the truth is the relativistic theory But we're going to go back to Newtonian days. And the reason we do it that way is to give you something interesting, hopefully, compared to what you normally do. So what we're going to study now is what's called small oscillations, or simple harmonic motion. It's a ubiquitous fact that if you took any mechanical system which is in a state of equilibrium and you give it a little kick, it vibrates. If you got a pillar, ceiling to floor, you hit it with a hammer, it vibrates. If you take a gong and you hit it, also vibrates. If you got a rod hanging from the ceiling through a pivot, it's hanging there. If you pull it, it goes back and forth. The standard example everyone likes to use is if you got a particle in a bowl, it's very happy sitting in the bottom. If you push it up a little bit, it'll go back and forth. And the example that we're going to consider is the following. If you have a mass, m, connected to a spring, and the spring is not stretched or contracted, it's very happy to be there. That's what I mean by equilibrium. Equilibrium means the body has all the forces on it adding up to zero. It has no desire to move. The question is, if you give it a little kick, what will happen? Well, there are two situations you can have. You can have a situation where a particle is on top of a hill. That's called unstable equilibrium, because if you give that a kick, it's going to come down and never return to you. That's equilibrium, but unstable equilibrium. I'm talking about stable equilibrium. That's because there are restoring forces. If you stray away from the equilibrium, there are forces bringing you back. And in the case of the mass and spring system, the force md to ma is equal to minus kx. And what this equation tells you is, if you stray to the right, x is positive, I'll apply a force to the left. Remember, this is ma and this is f. The f is such that it always sends you back to your normal position. So we want to understand the behavior of such a problem. We want to solve this problem. So how do you solve this problem? Well, I did it for you long back. When I gave you a typical paradigm for how you apply Newton's laws, I gave you this example. So I'm going to go through it somewhat fast. Our job is to find the function x that satisfies this equation. And we like to write it as follows. d2x over dt squared is equal to minus omega squared x, where omega squared is a shorthand for, omega is the shorthand for square root of k over m. By the way, I'm using big X and small x like crazy, so it's just small x. I don't mean anything significant between this and this. They're all the same. If you want, you can take this. Pardon me? Yeah, this is k, and this guy is k. And the other equation to use to follow the lecture today is these are all the same. Okay? So don't say what happened there when he moved from one to the other. All right, so what did I say we should do? You can make it a word problem and say, I'm looking for a function which, when I take two derivatives, looks like minus itself, except for this number. And we just saw that today. Trigonometric functions are the property that you take two derivatives, they return to minus themselves. So you can take a guess that x looks like cosine t, but it won't work. Than I showed you before, so I'm not going to go through that again. If you took this guess, by the way, this x is not a number. This x is a function of time. If you took this function of time, it in fact obeys this equation, provided the omega that you put in is the omega that's in the equation. Why? Because take two derivatives. First time you get minus omega sine omega t, second time you get minus omega squared cos omega t, which means it's minus omega squared times your x itself. And a is whatever you like. Then I said, let's plot this guy. When you plot this guy, it looks like this. And a is the amplitude. What is omega? Well, omega is related to the time or the frequency of oscillations as follows. If I start with t equal to 0, where the x is equal to a, how long do I have to wait till I come back to a? I think everybody should know that I have to wait a time capital T, so that omega times t is 2 pi. Because that's when the cosine returns to 1. That means the time that you have to wait is 2 pi over omega. Or you can say omega is 2 pi over t, or you can also write it as 2 pi times frequency, where frequency is what you and I would call frequency. How many oscillations it does per second. That's the inverse of the time period. So if you pull a mass and you let it go, it oscillates with a frequency which is connected to the force constant and the mass. If the spring is very stiff and k is very large, frequency is very high. If the mass is very big, the motion is very sluggish and f is diminished. So all the stuff comes out of the equation. One very remarkable part of the equation is that you can pick any A you like. Think about what that means. What is the meaning of A? A is the amount by which you pulled it when you let it go. You are told whether you pull the spring by 1 inch or by 10 inches, the time it takes to finish a full back and forth motion is independent of A. This frequency here is independent of A. Yes?
Is the small t over there the same as the big T?
This T here?
No, in the,
here?
at that point.
Ah, very good. That's correct. So let's be careful. So this is the T axis. This is the particular time, capital T. So the remarkable property of simple harmonic motion is that the amplitude does not determine the time period. If you pull it by 2 inches compared to 1 inch, it's got a long way to go. But because you pulled it by 2 inches, the spring is going to be that much more tense, and it's going to exert a bigger force so that it will go faster for most of the time. That's very clear. But the fact that it goes faster in exactly the right way to complete the trip at the same time is a rather miraculous property of the fact that this equation has this particular form. If you tamper with this, if you add to this a little bit, like 1 over 100 times x cubed, then all these bets are off. It's got to be that equation for that result to be true. Okay, so this is simple harmonic motion. Then you can do the following variant of this solution, which I will write down now. Suppose I set my clock to 0 right there. You set your clock to 0 here, but I can say, you know what, I just got up and I'm looking at the mass. I set my clock to 0. When it hits 0, it's not at the maximum. But it's the same physics, it's the same equation. And that really comes from the fact that we had one more latitude here of adding a certain number phi, which is called the phase, to the oscillator. Whatever you pick for phi, it will still work. And whatever you pick for capital A, it will still work. So whenever you have an oscillator, namely a mass and spring system, and you want to know what its x is going to be at all times, you need to somehow determine the amplitude and the phase. Once you know that, you can calculate x at all future times. So let me give you an example. Suppose an oscillator has x equal to 5 and velocity equal to 0 at t equal to 0. So what does that mean? I pulled it by 5 and I let it go. I tell you the spring constant k and I tell you the mass and I say what's the future x? You got to come back to this equation and you got to say 5 equals a cosine of 0 plus phi. And how about the velocity? Velocity is supposed to be 0. That is minus omega a sine omega t plus phi, where t is 0. So that tells me 0 is minus omega a sine phi. Omega is not 0, a is not 0. Therefore, sine phi is 0. That means phi is 0. You get rid of that. So the subsequent motion is x equal to 5 cosine omega t. This is a problem where we did not need phi. But it could have been that when you joined the experiment, you were somewhere here, then the mass is actually moving. Then I will say at t equal to 0, velocity was some other number, maybe 6. Then you got to go back and write two equations. One for x, take the derivative, which looks like this, and instead of putting 0, you put 6. You got two unknowns, a and phi. You got to juggle them around, and you got to solve for a and phi given these two numbers. It's a simple exercise to solve for them, and when you do, you've completely fit the problem. In other words, simply to be told a mass is connected to a spring of known mass and force constant is not enough to determine the future of the spring. You have to be told, for example, if nobody pulled the mass, it's just going to sit there forever. If you pulled it by 10, it's going to go back and forth from 10 to minus 10. So you have to be told further information to nail down these two numbers. They're called free parameters in the solution. On the other hand, no matter how much you pulled it and how you released it, this omega and therefore the frequency are not variable. Yes?
So any time you start at rest, the phi is going to be equal to 0, correct?
If you start it at rest, indeed it will be 0, because the velocity at t equal to 0 is minus omega a sine phi. If you want to kill that, the only way is phi equal to 0. You could put phi equal to pi if you like, but if you put 0, that will do. Okay, so this is the elementary parts of this thing, and I also already told you the following things. If x of t is equal to a cos omega t, now let's put phi equal to 0. In other words, we'll agree that since there's only one oscillator, it is perverse to set your clock to 0 at any time other than when the oscillator is at one extreme point. If there are two oscillators oscillating out of step, it's impossible to make phi 0 for both of them, because if you can sync your clock when one of them is at a maximum, that may not be when the other one's at a maximum. But with one oscillator, to choose phi other than 0 is perverse. It's like saying I'm doing a projectile problem. I'll pick the place where I launch the projectile to be x equal to y equal to 0. You can pick some other crazy origin, but it doesn't help. So we'll assume phi is 0 in this problem. If that is x, what is velocity at time t? Take the derivative of this, you get minus omega a sine omega t. That means the velocity is also oscillating sinusoidally, but the amplitude for oscillation is omega times a. So if a is the range of variation for x, omega times a is the range of variation for velocity. Velocity will go all the way from plus omega a to minus omega a. The acceleration, which is one more derivative, is minus omega squared a cos omega t, which is really minus omega squared times x itself. So the amplitude for oscillation for the acceleration is omega squared times a. So I think you should understand, if omega is very large, then the velocity will have very big excursions, and the acceleration will have even bigger excursions, because the range of this a really means if you plot x, it's going to look like this, going from a to minus a. This says if you plot the velocity, it's going to look like this. The range will go from omega a to minus omega a. If you plot the acceleration, it'll go from omega squared a to minus omega squared a. Last thing you want to verify is the law of conservation of energy. I think I mentioned this to you when I studied energy, but let me repeat one more time. If you take in this problem 1/2 mv squared plus 1/2 kx squared, I did that for you. You can also verify this. Okay? 1/2 kx squared is going to involve a squared cosine squared omega t. 1/2 mv squared is going to involve something, something, something sine squared omega t. And by magic, the sine squared and cosine squared will have the same coefficient. So you can use the identity to set them equal to 1 and get an answer that does not depend on time. That's the beauty. Even though position and velocity are constantly changing, this combination, if you crank it out, will not depend on time. And what can it possibly be? If it doesn't depend on time, I can calculate it whenever I like. So let me go to the instant when the mass has reached one extremity and is about to swing back. At that instant, it has no velocity. It only has an x, which is equal to the amplitude of motion. So that's the energy of an oscillator, 1/2 k squared. When v is equal to 0, x will be plus or minus a. At any other intermediate point, you can find the velocity if you give me the x. We did that too. So this is all I want to say about the linear oscillator. But let me mention to you another kind of oscillation, which is very interesting. Suppose you suspend a rod from the ceiling, like this. It's hanging there. If you give it a twist, then it'll go twisting back and forth like that. That's also simple harmonic motion, except what's varying with time is not the linear coordinate, but the angle theta by which the rod has been twisted. What's the equation in this case? Equation here is I d2 theta over dt square. You guys remember now that's the analog of ma. That's going to be equal to the torque. Now what will happen in the problems we consider is if theta is a small number, then the torque will be such that it brings you back to theta equal to 0. So this number will be approximately equal to minus some number kappa times theta. This is the analog of minus kx. Little k was the restoring force divided by the displacement, which produced the restoring force. Little kappa is the restoring torque divided by the angle at which you twisted it to get that torque. So this is always true. For small oscillations, since tau vanishes at theta equal to 0, it will look like some number times theta. If you like, it's the Taylor series for tau for small angles. If you knew this kappa, you are done, because mathematically this equation is the same as m d2x over dt squared is minus kx. Because the omega for this guy will be square root of kappa over I. You can steal the whole answer, because mathematically, mathematicians don't care if you're talking about theta or if you're talking about x. If you compare this equation to this equation, m d2x over dt squared equal to minus kx. If the omega there was root of k over m, the omega here will be root of kappa over I. So you may be thinking, give me an example where tau looks like kappa times theta. So I'm going to give you that example. So that example is going to be the following, a simple pendulum. Take a pendulum like this. It's got a mass m. It's got some length L. It's hanging from the ceiling. This is a rigid rod, not a string, but a rigid massless rod. And the mass m is at the bottom. So it's happy to hang like this. But suppose you give it a kick. So you push it over there to an angle theta, which is whatever you like. What is the torque in this particular case? Let's find out. The force is mg. And the angle between the force, and you're trying to do rotations around this point, this angle here is the same theta. So torque is really minus mg L sine theta. That's the formula for torque. It's the force times the distance of the lever arm, or the distance over which the force is from the rotation axis, times the sine of the angle between the direction of the force and the direction of the separation. So the equation of motion for the pendulum really is the following. I d2 theta over dt squared is equal to minus mgl sine theta. Now we cannot do business with this equation. This equation is a famous equation, but you and I don't know how to solve it with what we know. But we have learned even earlier today, look at the formula for sine x. Sine x begins with x minus x cubed over 3 factorial and so on. So if theta is small, then you may write it as mgl theta. So for small angles, sine theta is theta, and the restoring torque, in fact, is linear in the coordinate, the angular coordinate. So by comparison now, we know that this fellow is our kappa. So kappa for the pendulum is mgl. So kappa may not be universal in every problem. In each problem, you got to find kappa. You find that by moving the system off equilibrium, finding the restoring torque, and if you're doing that right, restoring torque will always look like something, something, something times theta. Everything multiplying theta is our kappa. So let's now calculate omega for the simple pendulum. I've shown you this is kappa over I, and kappa was what? mgl, and what's I? It's equal to moment of inertia of this mass around this point. The rod is massless. For a single point mass, we know the moment of inertia is just m times L squared. So you find omega is equal to square root of g over L, and that is 2 pi over t. So you get back the famous formula you learned. T is 2 pi square root of L over g. This is the origin of the formula you learned in school. It comes from small oscillations of a pendulum. So think about this problem. If you pull the pendulum by an angle so large that sine theta is no longer approximated by theta, but you need the theta cubed over 6 term, it can happen for large enough theta, then the equation to solve is no longer this. And what that means is, if you took a real pendulum with a massless rod and a bob at the end, the time it takes to finish an oscillation, in fact, will depend on the amplitude. But only for small oscillations, when sine theta can be approximated by theta, you will find whether you do that oscillation or that oscillation, the time is the same. But if you go too far, the other terms in sine theta will kick in, and the result is no longer true. The period of a pendulum, in fact, is not just a function of L and G, but also a function of the amplitude. Only for small amplitudes, you get this marvelous result. There's one problem I want you to think about. I may do it myself, or I think you should try to read up on it, and I will try to explain it next time, which is the following. I will give the problem to you, and I will do it for you next time, but I want you to think about it. Here is a hoop, like a hula hoop. It's hanging on the wall with a nail, and it's very happy to be where it is. Now I come and give it a little push. It will start oscillating. It will look like that, and sometime later it will look like that. It's going back and forth. Your job is to find the omega for that hoop. So you move it a little bit, and you find the restoring torque. Then you're done. But you've got to do two things right to get the right answer. You've got to find the moment of inertia of a circular loop, not around the center, but around a point on the circumference. So you guys know the magic word you got to use, parallel axis theorem. And to find the restoring torque, here is the part that blows everybody's mind. When the loop goes to that position, where is gravity acting? Gravity is acting at the center of mass. Center of mass is somewhere here in the middle of the loop, even though there is no matter there. So center of mass of a body need not lie on the body. The ring is a perfect example. So if you remember the center of mass of a loop is in the center of the loop, and put the mg there, you will get the right torque, and everything will just follow. By the way, my offer to you is always open. If there's something about the class you want to change, you find is hard, this, that, you can always write to me. Okay, I want your feedback, because I just don't know which parts are easy, which parts are hard, which are slow, which are fast, or if you haven't had enough math and you need some help. So send me some email, and I will try my best to answer that.